Um, Good evening, everyone. This is the interactive session for the NPTEL course Air Pollution and Control. Now, this session is for week 9 and 10 because the last two sessions we have done we have gone through the lapse rate. Now, in the lecture 9 series, the focus was on the different measurement techniques that are used in not measurement techniques, different techniques that are used in the measuring devices to collect the particulate matter or and they have different purposes. For example, oxidation, condensation, absorption, electrostatic precipitation, settling chamber, gravitational settling. All of these have different purposes, but these are principles that are used in different measuring device that we use globally to measure different air pollutants. Okay, so we go through some of the questions that are from that week, and then we move towards week 10. Week 10 has tutorial exercise, and then week 10 is not very difficult. It has basically questions on or discussion on different air quality standard, how they devise different methods of air quality, different legislations and acts. So for the week 10 I have had few questions, but the thing is that uh, since there are mostly tutorials of different questions or mathematical questions, I would say, then you can ask me from that perspective itself, that if you have any questions from the tutorial, you can ask and I will try to explain using the PDF. Other than that, let's start. Okay. So, the first question is about what are the natural self-cleaning properties of environment. Now, we know that if we talk about environment in general, nothing that goes to the environment stay there forever. Okay, unless and until it reaches stratosphere. For example, when we discuss ozone hole or something, we discuss something like CCl4 or chlorofluorocarbon and all these things. Since they have a lifetime and they can travel up to stratosphere, so we can say that okay, they stay for a long period of time. And for example, CO2, which has a higher time in the or long duration time in the atmosphere. Now, but there are other pollutants, for example PM 2.5, for example different gases which has very small lifetime in the atmosphere, and the smaller the lifetime there is, the it's easier for them for to remove them, right? So since we also devise certain methods to remove these pollutants from the environment, the surrounding also has its self cleaning properties. Okay, so first of the property is dispersion. Now dispersion is nothing but so what happened is that, let's say we consider a box, and then it has a lot of, and I fill it with gas. Okay, now the gas particles, they move around, they can freely move. And what if I put like a pressure on this box from the top, and now the particles start concentrated in one zone. Okay, so the thing is that the more freely particles can move, the more dispersed they are, right? So, and again, dispersion is a phenomena which happen or which depends on the meteorology also. For example, in summer, or you can say during the daytime or afternoon time, there is more dispersion because of the high temperature. Okay, so during the afternoon we know that the temperature of surrounding is very high. So the if in the previous series we have heard a term called mixed layer height, or sometimes we call it boundary layer height also. So what it is that we call this layer as like few kilometers above the earth's surface. let's say 1.5 2 kilometers above the earth's surface, there is a layer, okay, where majorly all the pollutants stays in this zone. Whatever we are emitting majorly stay here if it has a very short lifetime. Now this layer, the height of this layer changes between seasons and also between day and night time. Okay, so the height of this layer change depending on the temperature and humidity of the surrounding. So, and this layer again, it changes the dispersion, or how much particles will be dispersed in the atmosphere will change with the height of this layer. For example, in summer, the height would be, let's say, 2 kilometer or 5 kilometer, or let's say during afternoon the height would be 2 or 5 kilometer. But during the night time, or during winter season, the height decreases because the temperature also decreases. Okay. So dispersion is one of the phenomena for self cleaning. Next is gravitational settling, with or without flocculation of particle. Now flocculation is nothing but the stick, how the particles stick together. So flocculation is making a cluster of particles. So either particles settle itself due to gravitational force, or gravitational settling means that okay, the particle has a lifetime of 7 8 years, 7 8 days, and then after a while the speed of the particle is, let's say it's a normal particle without any flocculation. Okay, and it's moving here and there with the wind speed and everything, and let's say it reaches a place where the winds are calmer and everything, so it will settle on itself. Okay, so the time it reaches a place where the winds are calm, okay, it will settle. Similarly, if that is one way, but if it is the particle cluster together, make a flocculation, then also the size of the particle increases, and hence it will settle very fast even if there is wind. Okay, so the smaller the particle, it needs a calmer environment, or a less, like, extremely less wind environment to settle. And if the particle make a cluster, its size increases, density increases, it will settle even in a windy environment. Okay, so the gravitational settling, or the effect of gravitational settling changes with the type of particle also. Next is absorption. So absorption including washout and scavenging. So washout and scavenging is method that is used in wet deposition. So it is nothing but when, with the help of rain or snow, when the rain is coming from the top, and any sort of particulate or the gaseous matter that is there uh, in the region below the cloud, the rain will precipitate it and settle it down. Okay, that is what washout or scavenging is called. Scavenging is nothing but to remove something is called scavenging. So with the help of rain or snow, the water droplets remove the particles that are there in the atmosphere. Now you will ask that how will they remove gases? Okay, because you cannot see gas. The thing is that there is something called internal and external mixture, but the thing is that these particles, as their time increase in the atmosphere, they start making this bigger cluster, the flocculite, which we are calling. So let's say it's a pm 2.5 particle here. Then the what it gets in contact with the rain droplet, it makes this water drop sort of structure around it, and then on this the gases start trapping in this. So CO2 could be there, H2O could be there, nitrate could NO2 could be there. So they make this sort of we call this in our term like core and shell theory, or core and shell particle, where there is a particle center, and over which the gases trap on the particle, and the raindrop is stuck on the particle, and together they try to settle. Okay, because, and this phenomena is under comes under absorption. A rain out is same, that it's nothing, particles are there, the rain is coming, and they just deposited. The difference between absorption and rain out is that in absorption you are talking that a particle is taking the rain, okay, making this sort of structure with where the gas and the particles could absorb on that core, and then they are coming out. Rain out is nothing but particles are there and they are directly settling with the effect of rain. Okay. And next is adsorption. Adsorption is nothing but when the particle stick or the particles stick to surrounding another particle, okay, and that particle will come down to the earth. So these are five different self cleaning methods which are used, or which are effective in the environment. Next is how, or the list of all the pollutant removal mechanism. So these six different type of pollutant removal mechanism were discussed in the lecture 9. First is very simple, it's gravitational settling, is nothing but depending on the size of particle, it settles, and we measure it. So gravitational settling, um, so the heavier the particle, the it settle first, and the smaller the size of the particle, it will be more suspended. Okay, so gravitational settling works on that principle. Next is centrifugal impaction. So centrifugal impaction is nothing but when in a chamber, uh, if the air is moving in a center, and a centrifugal force is applied on it, then the particle start colliding with the wall, and then because of impaction, so if you see here two mechanisms are in play. One is centrifugal. Centrifugal is an outward force, okay, so it pull the particle apart. So if the air is moving like this, the particles are the pull of the particle is towards the outer side, you can say. And impaction means that because the pull is on the outward, it they collide with the wall and then they settle. Okay. Direct interception, so it depends on the inertia. Inertia is nothing that if a particle is moving, then until an external force is applied on the particle, it will not displace its position, right? So depending on how low the inertia is, or how low the movement of particle is, it will settle. So it depends on the uh, level of inertia of a particle. The heavier movement it has, the later it will settle. The less inertia it has, the faster it will settle into a chamber. Electrostatic attraction depends on that. First, you have a stream of air coming, you introduce into electric field. Okay, so whenever an air stream is introduced into an electric field, some of the particle attain, let's say, positive charge, another attains negative charge, and then they move into this electrostatic uh, chamber where one charged particle move in one direction and another charged particle move in different direction. So depending on, so first you are providing charge to the particle, making them positive or negative, and then you are separating it. Okay. Inertial deposition is same. One second. Okay. um, Inertial deposition is also same. It is that if the particle are moving, okay, and as the direction of the stream of gas changes, they will settle. Okay. So they have made it something like this. So if the particle is if the gas stream is flowing like this, and uh, Then as the gas moves in this chamber, the particles will collide with the wall, okay, here and there, and then as soon as they lose their inertia, they will deposit. Brownian diffusion works on the same principle, that the particle will move up, a barrier will be so in this, some barriers will be there in the path, and then the gas strike the barrier, the loses its inertia, and the particle fall. Okay, so these are the six different pollutant removal mechanism that comes into play, or that we use in the measuring devices. Next is collection efficiency. So whenever we study any instrument, for example, the easiest or the simplest instruments are the gas analyzer or the PM 2.5 sampler. The thing is that what how the so the principle of all of them depends on their collection efficiency, that how much particle or how much gas they can collect. The more the collection efficiency of a device, the better it is. Okay, so the collection efficiency is equals to 1 minus number of particle of diameter per meter cube of gas out, divided by per meter cube of gas in. Okay, so let's say one, because let's say an instrument has an efficiency of 100%. Okay, that everything that is coming, every particle that is coming in via gas stream, it is collected. Okay, so one is there, that is why one is taken. Next is we see that uh, how much particle is entering via, so gas here is nothing but the air the particle suck. Okay, so how much particle it is carrying while it enter the instrument, and when it exit the instrument, how much particle it carries. Okay, so let's say it has 50 particles, and when the air goes out, it has 10 particles. So based on that, we determine that what would be the collection efficiency, or how good a device is. Okay, next question is the minimum gas velocity required in settling chambers. So settling chambers work on the principle of gravitational settling, um, and they have nothing but they works on different principle. But the thing is, they have different levels, and a particle collect at different levels. So the simplest example of settling chamber would be, we have something called cascade impactor, or which we use for the indoor air pollution. So cascade impactor has different levels, and on each level a different fraction of particulate matter is collected. So that is what settling chambers are, that the heavier the particle, the farthest it will go, the lighter the particle, it will settle first. Okay, so for in any settling chamber, the minimum gas velocity or minimum air velocity should be less than zero point 0.5 meter per second for it to have a to work efficiently. Okay, next is how to increase the efficiency of a settling chamber. So what they do is that they increase, you can increase the height. Okay, the larger the size or difference between the horizontal trays, the better it is. And next is insertion of horizontal trays. So in between you include different what you different levels, so that there will be more impaction as it goes down. So there will be more different sizes, you can say. um, and in the inertial separator, same, which works on the principle of this direct interception or inertial deposition. The efficiency depends on the degree of impaction. The more uh, it impact each other, or the wall of the gas wall of the chamber, the better separation or better efficiently it will deposit the particle. Okay, because why it is so, because as they collide, they lose inertia. Okay, inertia, you can call that something has a tendency to move. now it collide with the wall or with among themselves, and they lose that ability to move and fall. So the more impaction there will be in a chamber, the better deposition there will be. Next is there is something called cyclonic separator. So cyclonic separator has something like this, where the air move in a spiral, and slowly the particles settle in this chamber. uh, so particles settle in this chamber sort of structure. Now the thing is, because it works on, let's say, two basic principles, not two, one is this, that is the centrifugal force, that particles are moving in the direction and the pull is outwards. um, Now effective efficiency, so if you want a cyclonic separator to work better, the diameter of the cyclone should be better, should be more. And that is why there is one thing there, that in some of the instrument they have, sorry, they have multiple cyclonic separator arranged in a series or parallel. So let's say this is a device, and they have like here like multiple cyclonic separator, and the gas is coming in this, and it's after some of the particle will collected here, then the gas move into another cyclonic separator, the particle will be collected here, likewise. So the diameter of cyclone, like this structure, the diameter of this structure determine the efficiency, that how much it can collect. Now they also there is also discussion about the fabric filter. Okay, so fabric filter generally, there are two different medias in which it is used. One is that in the houses we have this air purifiers, right? That they also work on this, they also have this fabric filters. Another is that in the offices and the institutions we have this central units, and that also have fabric filter. So fabric filter is nothing but filter which is in the form of mesh sort of structure, made out of cloth or different material, and they collect the particle which stuck to them. Okay, so but not one but multiple principle work on it. One is impaction, that a particle comes, fall on the or stuck the filter, uh, strike the filter and get stuck on it. Another is Brownian diffusion. If the particle is arranged, or sorry, the filter is arranged in a hello, okay, um, if the filter is stuck in the let's say in something, an apparatus, something like this, then Brownian diffusion can also help in the particle to get collected on the fabric filter. Next is electrostatic attraction. Of course, if along with the filter we have something like an electric field, and uh, because of the electric field the particles will get stuck to the filter also. So there are in a instrument which use fabric filter, a different sort of mechanism could lead to the deposition. Okay, that instrument can work on the principle of impaction, and after that there will be a fabric filter. Okay, so as the particle comes, they impact with each other, they fall on the fabric filter. Or an instrument works on the principle of Brownian diffusion, and after that there are fabric filters. So once the particle move, loses its inertia, they fall on the filter. And same for electrostatic, the particles get charged, get separated because of different fields, and then they got deposited into the fabric filter. The idea is that instead of a bin where the particle is collected, they have a filter on which particle is getting collected. Okay, simplest example is PM 2.5 sampler. So in that they have a sort of how would you say, they have a pump. That pump collect the air, suck the air from the atmosphere. The air moves into that pipe, and at the end of the pipe there is a filter which we call as quartz filter. We put that filter, and the air which is coming with the centrifugal force and undergoing impaction, okay, the particles start settling on the filter. So it's same, but it's you can say it's on the larger scale, because fabric filters are actually extremely large compared to a simple 47 filter. Okay. So these are the different mechanisms that can be used. Next is in electrostatic precipitator, what increases the collection efficiency below zero point 0.5 micron. Okay. So electrostatic precipitator, same. There are plates with different electric charge, and then based on the electric charge of the particle, they are getting attached to different plates. So now the collection efficiency depends for the less than zero point 0.1 micron particle, which is a very tiny particle. So if you want to increase the efficiency of electrostatic precipitator, there should be increased diffusion charging. Diffusion charging means that uh, the charge, there is more dispersion of the charge, or the charge changes, let's say. Okay. Sorry. Next is the wet scrubber. So next is wet scrubbing. So wet scrubbing is nothing but, depending on the there are different again. So those five principle that I discussed in the previous lecture, which is gravitational settling, impaction, diffusion, all of that. So wet scrubber also works on the same principle. In that, the another force which occurs in the wet scrubber is phoretic force. Okay, phoretic force, or uh, phoresis. So it is a force that depends on the uh, let's say, what do you call, how much water there is or stuck to the particle. Okay, how much water it can accommodate, let's say. When is I have no clue. So because we don't decide on exams. um, okay. So phoresis is, so there are different type of phoresis, thermo and diffuso. So thermophoresis is that, uh, so wet scrubber, as the name suggests, that a particle will get deposited based on, with the help of, let's say, water droplets. Okay. So this phoretic force comes when a particle has water or surrounded by water. So when a droplet evaporates, a particle which is saturated with water, when the water removes from it, okay, and the surface of the particle becomes colder. So let's say this is a water droplet that is there in a wet scrubber. Okay. And it has some of the particle which got stuck to, which got attached to the water droplet, because the air comes, the water is there, or the droplets are there, the particles got stuck to the droplet. Now you're increasing the temperature. As the temperature increase, the the water will start evaporating, but the particles will not. Okay. So as the water start evaporating, the particle there is in the droplet will start to accumulate, because if the droplet is bigger, the particles are separated. Okay. As the droplet, as the water is removed from this droplet, the size of this droplet decreases and the particles start coming closer together. So this is thermophoresis, that if a particle laden droplet is there, and you are removing the water from this droplet, then whatever particles are there, whatever aerosols are there in the droplet, they will start coming together. Next is diffusophoresis. It is a counterforce. It is opposite of thermo. So it means that this is, let's say this is the size of droplet, it has one particle stuck to it. Now you are putting more water to it. Okay, so if okay, so diffuso is that, let's say there are multiple droplets with different particles. So this is that I am evaporating uh, the water from it, and as I'm evaporating water, the particles are coming out of it. Okay, so in wet scrubber, either the particle could be collected in the form of clusters when the droplets is evaporating. Okay, so so let's say this is a plate, uh, a droplet comes which has lot of particles, the temperatures increase, the water start removing or evaporating, and the particles come together and make a cluster on this plate. Okay, another is that there are a lot of droplets with particles. Okay, they are not settled anywhere, and you are increasing temperature, so the water start evaporating here also, and as the water start evaporating, it it leaves the particle, right? So a particle which was stuck to the water, it is free because now you are removing water from it. Now these particles will settle as it is, they don't form cluster. They So diffuser is that there is a droplet with aerosol, you are increasing temperature, the water is evaporating, the aerosol is there, and aerosol itself is settling as individual, not as a cluster, or they are not drawn towards each other, which happens in the thermophoresis. So this is how they are different, or different methods of uh, used in wet scrubbers. Okay, then another method that was discussed is absorption. So absorption can be regenerative or non-regenerative. The name in itself suggests regenerative means that the material that is used for the absorption, so absorbing material can be reused, and here the absorbing material can't be used or reused. So is for this, of course, absorption happen on a very large scale, or there are very heavy instruments which also use this principle of absorption. But the simplest example of understanding the difference between regenerative and non-regenerative evaporation is, so in our labs there is something which we call as desiccator. Okay, so the principle of desiccator is that it is a two, it's nothing but a plastic box with about 300 mm. Okay, and it is a basic so there is a plate with holes, bigger holes in it, and here what we do is we have this something called silica. Okay, so desiccator is used, and on, so this is nothing but a plate with holes. So in this, uh, in the over that plate we put our filters, or we put our samples from which we have to remove the moisture. Okay, so the thing is, desiccator is used to remove moisture from any filter. Okay, so in this silica helps. So what we are doing is we are putting silica at the bottom, then we have this plate over which we are putting our filters and everything, we are covering it. So now it's a compact system, and over time it removes any moisture that is there in the filter that got absorbed on the filter surface. So if you have seen silica, the initial color of silica is blue, but as the time passes, as the silica works, the color changes into white or transparent. Okay, but the thing is, this silica can be reused. How? We take out the silica, we put it on a tray, and we put that tray into for baking. Okay, we put it into an oven for some time period at 100 degrees Celsius, and we let it uh, bake there for a couple of hours, and the silica regain its color. It will not become extremely blue, which it was, but it can be used like couple of times. It attains some colors of blue. Okay, like light blue or something, it becomes, you use it again. Okay, so you can use silica, which is an absorber. It is absorbing moisture multiple times in a desiccator. So this is the easiest example of regenerative what's the- okay. This is the easiest example of regenerative absorption. Now next is the why it is important in absorption process to not reach equilibrium. Okay, now if in an absorption, let's say you reach equilibrium. Okay, so equilibrium means that to and fro are same. Okay, so for example, in osmosis you see, however much I'm adding, it is removed. Okay, so if the equilibrium is reached, then uh, the gas that is absorbed will again, or the gas which is liquefied will again become gas. Okay, and if this happens, then the absorption, there is no point of absorption. If there is, let's say, silica, if it is absorbing moisture. Okay, moisture is nothing but uh, water vapor, right? It's a gas. It is absorbed on a on silica. Now if after some time, if the equilibrium is reached, then this silica will start removing it, whatever moisture is has accommodate. Okay, and then silica will become blue, and the moisture again comes to the desiccator. Then there is no point of absorption, right? That whatever you are absorbing or uh, liquefying, again becoming gas. So if this happen, then it's null. The whole concept of absorption in the environment or in environmental instrument will be nullified. So that is why, to avoid this gas to transfer mechanism, we have to avoid equilibrium. Now the last lecture is about oxidation and condensation. So uh, generally oxidation is a technique that is used for organics. Okay, so what you are doing is that in industries where there are a lot of, or not industries, in for example, there is a lot of methane, ethane, or benzene, like hydrocarbon like structure. Okay, is there or released in the atmosphere. Now if that happen, then uh, there will be a lot of, again, hydrocarbon is a type of pollutant, right? Benzene is a type of pollutant, methane is a pollutant. So what it does is that you have a lot of hydrocarbon in the atmosphere. You take that and you oxidize it into CO2 and water. This is how oxidation, any oxidation technique works. That you take hydrocarbon, you oxidize it into carbon dioxide and water. Okay, so it is a good technique to remove organics. Now there are two different types of oxidizer system. One is the high temperature gas phase oxidation system. So here you have a gas, which a high temperature gas, which actually help in oxidizing the compounds. So if you have seen this, we use some an instrument, some which is called as the organic carbon and elemental carbon analyzer. It has this high temperature gas pass through it, which actually helps in the this conversion to CO2 and H2O. So that is one. Another is catalytic oxidation. So catalytic is that there is a catalyst which enhances the process or which initiate the process of oxidation. So these are two different oxidizer system uh, which is used in instruments. Next is the second type of method, which is the combustion. Sorry. Okay. So another thing is that in a in an instrument or oxidizer system, what are the condition that is required to complete this combustion? So this is nothing but you're combusting a gas, a hydrocarbon, right? So first is temperature. So the higher the temperature, the more burning there will be. We know oxygen is flammable. Next is uh, the material should respond to oxygen, right? So if it's not a combustible or if it's not a flammable material, it is of no use, or it cannot, the oxidation or oxidizer system cannot be used. Next is there should be sufficient oxygen supply, and another is the residence time of the gas is long. Okay, the gas that you are burning should be long, so that um, the oxygen uh, easily be able to combust it or burn it. Okay, next method is condensation. So it is to recover the organic compounds. Okay, so um, in the industries there are certain hydrocarbon which are released, which are important. Okay, so instead of releasing them into the atmosphere, what industries want is that let's do one thing, that whatever exhaust we are emitting or whatever waste we are generating, if it has material which can be used or which can be of benefit to us, they do this recovery. And this recovery is with the method of condensation. So condensation is a, when we have studied this in 11 12 also, we know that we heat a substance. Okay, it becomes vapor, then you that thing enter into a chamber which has a very low temperature. So what it does, it condense. Okay, so the same principle will work. You have waste or organic waste, I will call it. Okay, you keep it to a very, let's say you reach it its temp a what do you call it, let's say a boiling temperature or a temperature where it will become vapor. Okay, vaporization temperature, let's say I call it. So you have an organic, you heat it until some of the part which we want to recover, they reach their vaporization temperature, they convert to vapor. Okay, then they enter a chamber which has a very low temperature. In this chamber, as they enter, they condense, and as they condense, they settle, or they e- enter into a, or they settle on a plate or a dish, whatever there is. Or a beaker, whatever. So they settle, and whatever is non-vaporized, or if a gas is cannot be converted into, or cannot be condensed, it passes from here. So it depends on the vaporization temperature of the organic compound that are present in the organic waste from the industries. So first you increase the temperature, convert to vapor, then put it into a chamber with very low temperature, and then let them condense. And it functions, or it work well, because every particle has a different vaporization temperature, right? It convert at different temperature, it convert into vapor at different temperature, and similarly it condense at different temperature. Okay, so then you can have these multiple chambers where different organic waste will be condensed depending on the temperature of the chamber. And there are different type of condenser system discussed, and one of them is a surface condenser. Okay, so uh, in condenser system, they, one way is that you just increase the temperature of the surrounding. Okay, so some people use this, some people generally use, or the simplest is water. Okay. Um, so you have very cold water or cold ice, and using that you are condensing the particle. The other is generally use something called gas. Okay, which is nitrogen gas, which help in, or which has a very low temperature, so it helps in the condensation. So this shell and tube structure is nothing but in a chamber, there are something like this. Okay, a tubing sort of structure. Okay, and let's say a stream or the vapor enter here. They have this tube which have, let's say, N2, and the stream enter, and because of this tube, which which is, it's not directly, so the gas is not directly affecting the organic compound or the vapor, but it is in the tube, so the tubes are cold enough to help the vapor settle. Okay, so this is a shell and tube, that you have a shell and you have tube, and that is the surface condenser, or they condense on the surface of the tube. It is also indirect condenser because the gas or the low temperature liquid or the low temperature gas, which is N2, did not come in direct contact with the vapor. Okay, now after this, it's about the air quality standard. So this question is that what are the various component of air quality standard. So the four components you need to remember. One is the indicator. Indicator is any gas or particle that we are studying: PM2.5, PM10, SO2, NO2, benzene, ozone, etc. Whatever. Averaging time is that, if you have seen the NAAQS list of different standard, for some they have an 8-hour average, for some they have 24-hour average, for some they have 1 day average, etc. So depending on how toxic they are and how much measurement they have different averaging time. Then next is form, that in what form they are understanding or measuring it. And last is the level, that what are their level, what are the ppm values that we use to constrain them. So for example, SO2 is, let's say, 15 ppm. So anything in any environment, if SO2 is above 15 ppm, it is harmful. If it is below ppm, it's okay. So all of these four parameters help us understand or define the air quality standards. Now there are different factors which affect, which help us to understand the air quality standard. So if it is uh, so how a pollutant can be defined, that it should be constrained. Okay, so it depends on, is it affecting the health, is it affecting the population. Dose response curve, it means that how much intake would actually affect the people. Okay, so for example, if let's say a pollutant has, let's say, even if it goes 1000 ppm in the environment, it will not affect. Okay, for example, gases like N2, O2, even if their concentration is high in the atmosphere, they does not affect us, right? Because our body will not get affected by the high oxygen concentration around us, or high like at a certain level, it will not be affected. But if let's say SO2 or NO2 or PM concentration increase above a certain level, then our body will start reacting. Okay, some people have this asthma thing. So, or it also depends on this, that a healthy individual will have a different dose response curve, because let's say I can take up to 100 ppm of PM 2.5 and I will not be affected, or my symptoms will not be shown. But if a person has asthma or has a respiratory disorder, then this dose response curve will be very low. They can maybe they show symptom even at 20 ppm. Okay, so depending on the type of individual or the type of compound, this dose response curve vary. So we need to understand that also. Next is exposure characterization. So, for example, how much a person is spending outside, how much time that person is spending indoors, in offices, in industries, like So depending on that, how much depending on the region or where they are working or staying, their exposure changes. So that we also need to understand. And same for the old age, the exposure value would be very low, but for a young generation it would be high, because they can intake a high or large amount of pollutant and still show less symptom compared to a old person or a child, for example. Then we need to understand the risk assessment. Risk assessment is that how much, with how much intake, how much risk are involved. Okay, with 50 ppm how much my body will be affected, with 100 ppm how much my body will be affected, and then how you will we will rectify that intake. Next is acceptability of risk, that at what level or threshold it's okay, like people are okay that if they take, let's say, 50 ppm, irrespective of their age, gender, disease, they will not be affected. That is the acceptability of risk. Okay, so next is that why this is the so this is dose response curve. The thing is why it is important, because it help us understand that how with the change in the level of toxicity. So dose is that how much pollutant you are inducing in a body or you are incorporating in a body. So with the change in the toxicity of various substance, how the how the response or how the body changes, and it help us understand or establish the air quality criteria. As I said that if for young it can be 50 ppm, for an old it can be 5 ppm, depending on different factors. And now this thing can come that there are different points in the dose response curve, these 4 points. And what are those? So this A point is the threshold. Okay, threshold is nothing but the minimum amount a person need to inhale or intake for it to show effect. Okay, so let's say I am in an environment and I am taking every day, I'm taking 50 ppm of PM 2.5, inhaling it, no effect. Let's say next day there is lot of pollution and it goes 100, let's say no effect. Next day it becomes 150. So on 150, let's say I start having cough or sneezing. So threshold is the minimum amount that is required uh, for the response to show, for the effect to show. Then B is the point of or the value of maximum sensitivity. Why maximum sensitivity? Because this is a increasing curve, right? Though, so at this point a slight change in the dose would change the response. Okay, that is the the point or the curve of maximum sensitivity, that with slightest change there is change in the response as well. And C is the point of maximum dose. Okay, when the dose at which maximum response is there. And D is the point after which you don't see, like, let's say D is a point when a person dies. So after this is the maximum dose a person can take. This is the limit, or you can say the limit of dose a person can take. So these are the 4 points. Next is what is the first act of independent. Next is about these acts. So there are a lot of acts, and in the I have discussed some of them in the previous series also. So here I am just discussing few of them. So first, this is about the first act of independent India, which is focused on air pollution. So you can remember it's Factories Act 1948. Now there is something called Rengelman chart that is discussed there. So it is used to understand. So based on the color of smoke, they have defined the type of level of pollution. Okay, so they have devised a chart. And what people do in that time, that based on that what is the color of the smoke that is coming out of chimneys, they determine if this smoke is harmful or is it okay, or within permissible limit. So that is why Ringelmann chart is used. And the last is the Air Act 1981. So it is important because it is the first act which is uh, formulated to provide the prevention, control, and the abatement of air pollution. There are a lot of act and series or timeline of different legislation. You can go through them, but it's, you have to remember everything. Like, it's something that you have to uh, remember. There is nothing too much to understand in it. So for today, we are done. If you have any questions, you can ask. um Otherwise it's okay. uh, Phoretic forces you want again, Pragya? Shall I explain again? Okay. So phoretic force is a phoresis is a term that is used, wait, for the, wait, mm, just a second. Essay type is nothing but you have to, like, for some of these things you remember, right? That for example, as as easy as uh, what is wet deposition, so you can answer that what is wet deposition, how wet deposition is done, right? So I think that is essay type. Compute Computer pay, I think you can type, right? Or they give that, so what they do is, uh, I think what they do is that they have a sheet after every question which is essay type, and there in that blank you can type 50, 100, 200 words. I don't think it will be like 1,000 words. Essay type means generally that you have to give descriptions of the questions. Okay. Is there will be, so there is no essay type. Okay, then that is good. But it's just that if they have written essay type, you should be able to, I think, explain, like, if they ask what is wet deposition, or if they ask that, like, you need to remember some of the definition, that would be, I think, helpful. Agar if there is mail, then I think in the format it's like essay type also, right? In the format it's written. Okay, then just remember, like, just read it. uh, I don't think it will be 500 or 1,000 word. I think it will be one or two liners. It won't be much. So I, and they will give space, so I think it will work maybe. um okay, so the for I will explain phoresis and then you're done. So phoresis is a term that is used to define that a droplet, or a particle laden droplet, I would say. Particle laden droplet. So how in this, so this is a raindrop, it has particles. So if a force, is acting on this, they call it phoretic force. Okay, phoresis is a term that is used for water. So thermo and diffuso, the difference is, in thermo, let's say a droplet is there and it has lot of particles. The uh, because of temperature, the water start evaporating, and since the size of the droplet decreases as the particle as the water start evaporating, so the particle there in the droplet, they start coming closer and they make a cluster. Okay, this is thermophoresis. You are heating, the droplet is has lot of particle, but since the water is evaporating, the particle are coming closer, making a cluster. Okay, diffusive is that there are a lot of particles with let's say one there are a lot of droplets with particles. Okay, they are not coming together, the particle are not coming together. As the temperature is increasing, the water is evaporating from these droplets and they are depositing in the form of tiny little particles. So there is no, you can say there is no coagulation or flocculation in diffuso. On the other hand, in thermo, there is this coagulation or flocculation. Okay, so this is what the difference is. If you have any other question, you can ask. Otherwise, we are done for today. Yeah. So, see, the thing is that in those, all I can do is that, like, all you can do is they have given some formulas, right? And they have, like, in the lectures also, there is no explanation of the formula. They are like, okay, for condenser system, this is the formula for collection efficiency, this is the formula for settling chamber, this is the formula of diameter, and all you have to do is, there are questions and you are putting the formula, uh, solving the question. Now, how I think you should approach is that, take a sheet of paper. Okay, whatever formulas are there in the entire series, okay, in the entire, note down just the formula and what are the different terminology means, diameter, flow rate, or wind speed, whatever it means. And then when you come to the numerical part, you have that sheet ready, and then go through the numerical. I think that is the best way possible, because every numerical has a formula which there is no explanation of how this formula has come into play. There is no description of it. So you have to remember or memorize the formulas. There is no other way out. Yeah. Okay. So if it's if no one has any question, then we can end it. uh, Thank you everyone.